Early on, we talked about the idea of doing bubble and dew point calculations. And we talked about this within the framework of ideal binary vapor liquid equilibrium, right? Using Raoult's law and our material balances in order to ultimately, for example, calculate the vapor composition at a particular temperature and pressure from the liquid phase composition at the opposite, either temperature or pressure, depending on whether we were doing a bubble point temperature calculation or a bubble point pressure calculation. We could do the opposite with dew point calculations, right? Here the idea is we're trying to calculate the liquid phase composition values from the vapor phase composition values, again, at pressure or temperature, either way, depending on the nature of the calculation that we're looking to do. So, in ideal binary VLE, this worked out to be a 4 equations and 4 unknowns problem. And we've talked about, we've seen examples, we've worked on this particular problem before. Now the challenge that we're facing is how do we extend this to situations where things are a little bit more complicated in terms of having perhaps more components in the system, which is what we're seeing when we start doing multi-component distillation type problems. Additionally, we might be in a situation where we want to relax that ideal assumption and we don't want to use Raoult's law anymore. And so we're going to think about a situation where we can use the K values to do bubble and dew point calculations. And the idea, at least from a conceptual perspective, is going to stay relatively the same, but the way that we'll set up the equations or the way that we'll approach the problem is going to look a little bit different compared to the situation when we were using Raoult's law. So we'll remember, and it's important to keep in mind, right, that these K values defined for a particular component are functions of temperature and pressure, right? So if we go and look through WANCAP, for example, equation 2-28 gives us an expression for the K values in terms of temperature and pressure. The de Priester charts give us that information. But we need to keep in mind that K depends on T and P, right? And so that's going to be very important in terms of doing these calculations. We also need to recognize that K, right, is, again, the ratio of the vapor phase composition to the liquid phase composition. And this gives us the VLE information, right? If we have the K values from the de Priester charts, we don't need Raoult's law. We don't need a more involved VLE expression because the K value itself is the equilibrium information that we need. And so we want to think about how do we use K values now to start doing bubble and dew point calculations. And the thing that we want to think about is the solution procedure when we worked with Raoult's law is going to be somewhat similar, right? If we think about how we worked through the Raoult's law examples for bubble or dew point calculations, the way we typically did this was to use the material balances to sum up the mole fraction of the component that we don't have, right? Because we know that the sum of those has to go to unity. And then solve for either the temperature or pressure, and then go back in and calculate the remaining mole fractions based on the temperature or pressure that we now know. And so, for example, if we're talking about doing a bubble point calculation, we don't know the vapor compositions yet. But we do know, it's just right here, bubble point calc. We do know, in this case, with the bubble point calculation, that the sum of all of the y sub I values has to be equal to 1. And now if we think about how this plays out, right, we could also say that this then means that the sum of all of the K values times the X, or liquid phase compositions, also has to equal 1. Right? And so this is how we start to incorporate the K value-based equilibrium approach into our bubble point calculations. And so now if we're doing a bubble, say, a bubble T calculation at constant pressure, right? We might know our pressure from our distillation problem, for example. Now what we're looking to do is to solve 1 is equal to the sum of the K values, and I'll just write out again the explicit temperature, say maybe pressure of the column, if we're doing an example here, but it could be some other pressure depending on the circumstances. And the liquid phase compositions that are known in setting up this problem. And so in going through and doing this, then for as many components as we have in the system, we could write out the number of terms we need on the right-hand side of the equation. Remember, go back to WANCAT equation 2-28, right, to refresh our memory about the fact that for systems where we know the K values as a function of temperature, right, ultimately that K as a function of temperature is just some mathematical expression where T is the only unknown. We're given X in the bubble point calculation approach to things. We're given P if we're doing a bubble temperature calculation. And so in this expression we have here, we can do the bubble T calculation because the only unknown, if we write this out for however many components we have, is simply going to be the temperature. And so we might have a very nonlinear problem that we need to solve, but ultimately at the end of the day, we could do that math. And we could use goal-seek to use unity as our criterion for achieving our final answer in terms of the temperature for this bubble temperature calculation. And then we could go back in, right, and we could evaluate for each component the K values at the solved temperature that we just found through our bubble T first step of our calculation. And for each situation, right, we could multiply the K value at that temperature we solved for at our pressure, and we use the X value that we're given, right? And so then we could solve in the rest of the Y values and finish off the bubble temperature calculations. The same approach is going to be the case with dew point calculations, right? So in this case, we're just going to do the opposite. In the dew point calculations, we don't know the X values, but we do know that those liquid phase compositions all need to sum to unity. And so this is going to tell us that also we could come in and have a situation where we sum up all of our yi values divided by the K values. Right? And this would get us now a situation where we have an equation that would allow us to do dew point calculations. And we could do the same thing. A dew temperature calculation here would require us to put all of the temperature-dependent K value information in. We have the Y values from the problem statement, and the only unknown we have here is temperature in the dew temperature example. And we'd have to go through and do some sort of nonlinear solving algorithm in order to work that out. But that's math that we know we can do, or we can set up Excel or MATLAB or Mathematica to do that math for us. And so what we want to get at here is this idea that these bubble and dew point calculations that are going to be important for multi-component flash or multi-component distillation balances can be done using the K values. That relaxes the ideal assumption, right? We're not assuming ideal VLE here. And we can do exactly the same sorts of calculations that we did with Raoult's law, just now in a different flavor. This also comes back to the thing I said weeks ago now, where it's, this handful of VLE calculations, right? The dew and bubble point temperatures and pressures, the flash calculations, the PNT calculations. These 6 VLE calculations are what we do for everything. It's just a question of how we structure the problem given whatever the vapor-liquid equilibrium information is that we have. And so I want everybody to be familiar with extending this idea of the bubble and dew point calculations now in terms also of K values. Point out here that the math gets a little bit easier if alpha is a constant. So if alpha ij, which again is equal to ki divided by kj, if this is a constant, then things get a little bit easier. And remember, we said that sometimes the relative volatility ends up being more or less constant because the temperature and pressure dependence of the K values ends up dividing out when we do this division of Ki divided by Kj. So in some cases, a constant relative volatility, ends up being relatively reasonable. And so in these situations, we have a situation where, we can go through and do our bubble point and dew point calculations by assuming that the alpha ij values are constant. And so, for example, if we're going to go through and do this, now we don't have to go through and do the explicit temperature calculation, for example, because the alpha value is taken to be independent of that. So right away we see that if alpha ij is a constant, that temperature or pressure dependence divides out, and that immediately makes things much easier for us. And so in this case, if we're doing a bubble point calculation, for example, here we're looking to solve for yi as a function of x. And so for a multi-component system, right, we'd have a situation where we might have something that looks like this. And we'll talk a little bit more about this as we go, but if we do have a multi-component system, we need to define alpha relative to some reference component, and we can pick that to be any one we want, but ultimately we'll need to pick one of our components as the reference that we use for all of the calculations. But in this case, then we could go through and do our bubble point calculation for any number of components in the system under the assumption that alpha ij, or under the condition, I should say, that alpha ij is actually a constant value. And likewise, we could go through and think about what a dew point calculation would look like here. And of course, that's going to be somewhat similar in terms of the structure of the examples that we're going to talk about. All right, and so, in this case, we can think about how we would extend bubble and dew point calculations to this special case scenario for multi-component systems where that temperature and pressure dependence divides out when we divide out the K values to define alpha. Again, just as a reminder here, this reference component, we're just saying that this is going to be some K value of the component of interest divided by K of a reference component, and that'll just be one of the components in our system. We get to pick, and as long as we're consistent, it doesn't matter which component we choose as our reference component, but we'll see how that works out as we work through a few examples of this type.